Hello everyone, I am Payal Likhar and in this session I am going to discuss about SoC verification. So what is verification? Verification is a process used to demonstrate the functional correctness of a design. Verification is for to making sure you are verifying that you are indeed implementing what you want. It is to ensure that result of some transformation is as expected. Verification methodology: verify that the blocks have been connected correctly and perhaps run a few simple tests to verify that each major block is functioning. There are some problems during verification. They are: was the specification correct? Did the design team understand the specification? Was the block implemented correctly? Were the interfaces between the block correct? Does it implement the desired functionality, and so on. So now let's see what is the difference between testing and verification. Testing verifies manufacturing. It verifies that the design was manufactured correctly. Testing is executing a system in order to identify any gaps, errors, or missing requirement in contrary to the actual requirement. Next comes SoC design verification. Using predefined and pre-verified building block can effectively reduce the productivity gap. Verification portion of design increases to anywhere from 60 to 80% of total development of effort from a design. One of the important questions is, when is verification complete? We get some answers from real designer, which are: when we run out of time or money, when we need a shift to product, when we have exercised each line of a HDL code, when we have tested for a week and not found a new bug, and we have no idea when it is completed. Designs are often too complex to ensure full functional coverage. There are some approaches in verification. They are top-down verification approach. It is from system to individual components. It contains system specification, then system design. In between system specification and system design is a system level verification. In system design, hardware IPs library and software IPs and RTOS library is present. After the system design, hardware-software partitioning is done. Then synthesis chip plan and design with the netlist verification, and then functional verification, timing verification, and the device test. Second is bottom-up verification approach. It is from individual component to system. It contains some level testing like component, block, unit level testing, memory map, internal, interconnect level testing, system level testing, etc. Next is platform-based SoC verification approach. It verifies to develop IPs in an existing platform. Interconnect verification between SoC platform and newly added IPs. Fourth is system interface as driven SoC verification. It models each block at interface level. Beside design under test, all other are interface model. It is suitable for final integration and verification. In verification, testbench environment commonly used. It contains stimulus generator, that is input pattern, then design generator, design under test, that is DOU, and response checking, that is output. Definition of test bench is a verification environment containing a set of components and the interconnect of such a component with the design under verification. Components such as bus functional model, bus monitors, memory model. In test bench design, auto or semi-stimulus generator is preferred. In that, automatic response checking is highly recommended. You may be design test bench with different techniques, that is test bench in HDL, test bench in programming language and interface. Design with waveform based, design with transaction based, design with specification based. Types of verification test is random testing, functional testing, compliance testing, corner case testing, real code testing, and regression testing. Verification plan is very important. It is a part of design report content. Test strategy for a both block and top level model. Verification plan required verifies tool and flows, simulation environment including block diagram. Key feature needed to be verified in both the block and the top level. Because of verification plan, there is a clear criteria to determine whether the verification is successfully complete. Benefits of verification plan is it develops test bench environment early, it tests suits developed early, it develops the verification environment in parallel with design tasks by a separate team. It enables to focusing the verification efforts to meet the product shipment criteria. It also enables designer to think through the time-consuming activities before performing them. There are a number of verification tools. Simulation is one of the tools for verification. It contains simulators like event driver simulator. It is for accurate timing. Second is clock-based simulator. It gives faster simulation time. Transaction-based simulator. It requires bus functional model of each design. It only checks the transaction between components. Code coverage. Code coverage-driven verification can indicate how much of design has been exercised, and it points out what areas need additional verification. It qualifies a particular test suite when applied to specific design. It verifies more but stimulates less. Test bench automation requires both generator and predictor in an integrated environment. Generator constrains random pattern and predictor generate estimated outputs. Testbench is a platform providing powerful construct for generating stimulus and checking response. Next is an analog or mixed signal (MMS) simulation. It is an analog behavioral modeling, a mathematical model written in a hardware description language. It emulates circuit block functionality by sensing and responding to circuit conditions. Available analog mixed signal HDLs, Verilog A, VHDL-A, Verilog AMS, VHDL-AMS. Static technologies are lane checking. It is a static check of a design code that identifies simple error in the early design cycle. That is, it avoids error code that increase design iteration. It checks for a built-in or user-specified rules like testability checks, reusability checks, etc. Static time analysis. That is STA. STA is a method for determining if a circuit meets timing constraint without having to simulate. It checks timing related problem without input pattern. Next is formal verification. It checks functionality only. Primary application are equivalent checking, model checking. It solves completeness problem in simulation-based method. Formal verification cannot handle large decisions due to its high complexity. Theoretically, it gives promise for 100% coverage, but design size is often limited due to high resource environment. It is valuable but not general solution. Hardware modeling are a pre-developed simulation model for other hardware in a system. In this, hardware accelerator is used to speed up a logic simulation by mapping gate level netlist into a specific hardware. Emulation. It is verified design using real hardware like FPGA. It gives better throughput in handling complex design. It requires expensive emulator. Next is rapid prototyping. FPGA prototyping. It degrades the performance. It has limited design capacity in FPGA prototyping and routing problem prototyping occurs. Now we talk about SoC verification flow. First we see SoC design flow. The step for SoC design and verification is shown in this flow graph. The design is given step by step. First, system specification is